Okay, so hello everyone. Welcome to Audit course session number 10. Today's topic is Darlington Emitter Follower Amplifier. Emitter follower other name is Common Collector Amplifier. Okay, so this is a common collector configuration, but here we have used Q1 and Q2 form a Darlington pair, as you can see over here. So this is my circuit. So we have over here R1, R2, RE, the three resistors, the two coupling capacitors CC1 and CC2, which couples the input AC to the input of the circuit, and you can take the output from this emitter terminal after connecting the coupling capacitor. And the entire circuit is powered with plus 10 volt supply. Okay, so we have to do the DC analysis, find all the terminal currents and the voltages, then find the small signal parameters, and finally find the midband gain and the voltage gain and the current gain also in this case. So let us start. So first of all, we will do the DC. We will draw the DC equivalent circuit. So for the DC equivalent circuit, all the capacitors will behave as open circuit because the reactance offered by the capacitance is 1 upon 2 pi fc. So for DC, the frequency is 0, and the capacitance offered by the reactance offered by the capacitance will be infinite. Hence, they will be treated as open circuit when we do the DC analysis. So this is my DC analysis circuit. So I've just marked the terminals over here, collector 1, C1, B1, E1. The emitter terminal of the Q1 is connected to the base terminal of Q2. So E1 and B2 are same. Then we have C1 and C2 are same, and we have E2. Okay, so this is the DC equivalent circuit, and we can apply the Thevenin's equivalent at the base terminal, that is as base 1, and we can determine the various parameters. So let us start. So one more thing you will need to remember that the VBE, the base to emitter voltage for both the transistors collectively is capital VBE, okay, which is the addition of VBE1 plus VBE2. Okay, individual transistor VBE voltages will be added up over here. So I'm assuming that you all have gone through this Darlington emitter follower amplifier configuration in your theory lecture. Now let us concentrate on getting the simulated value and the calculated value ready with us. So let us start. So the given is beta 1 and beta 2, that is the current gain for both the transistors are given as 100, and the VB1 and VB2 is 0.7, but which is also taken over here. Okay, so the total VB, as I've told you, it is a combination of VB1 plus VB2, so that will be 1.4 volts. Okay, and your VTH, I told you all that we can apply a Thevenin's equivalent at the base terminal. So after doing that, your VTH will be R1 parallel to R2. VTH will be R2 divided by R1 plus R2 into VCC. Okay, as we applied many times before, and RTH will be R1 parallel to R2. So that's what we write over here. Your VTH or VB1 will be R2 divided by R1 plus R2 into VCC. And R1 and R2 values are 50 and 100K. Okay, and VCC is 10. So if you put those values in the calculator, you will get VTH as 3.3333. Okay, volt. Now RTH will be 100K parallel to 50K, which is R1 parallel to R2, which will be 33.33 kilo ohms. Now, IBQ1, there is the current flowing into the terminal, base terminal of transistor Q1 is given by the formula VTH minus VBE divided by RTH plus 1 plus beta square divided by RE. So you have to remember that in this formula, we have 1 plus beta square. So we substitute all the values, beta is 100, so 1 plus beta will be 101 square over here. Okay, because we have a square term. So if you put all the values together, IB1Q value will be 0.1889 microampere. So just confirm this value in calculator. Remember VB here is not 0.7 but 1.4. Now next, once we get the value of IB1, we can easily get the value of IC1, which is beta 1 times IB1, which will be 100 into 0.1889 microampere, which will be, if you get the number, you will get 0.01889 milliampere. Now, the emitter current IE1 will be IC1 plus IB1, that will be 0.019 0.08 milliampere. Now, from the circuit, IE1 and IB2 are same. Okay, if you see carefully, IE1 and IB2 are same. Okay, so the value of IB2 also will be 0.01908 milliampere. Now IC2 is beta 2 times IB2. So if you multiply that, you will get IC2 as 1.9079 milliampere, and IE2 will be IC2 plus IB2, which will be 1.927 milliampere. Now, the the voltage at the emitter terminal for a transistor Q2 will be VE2 is IE2 into RE. So if you multiply that, you will get 1.927 volts, and VC2 is 10 volts itself. Okay, if you see carefully, your VC2 is nothing but you're connected to your power supply of 10 volt. So VC2 will be 10 volt only, whereas VE2 will be IE2 into RE. So that's what we have calculated over here. Okay, VE2 is IE2 into RE, which is 1.927 volt, and VC2 is 10 volt. So VCE2 will be VC2 minus VE2, that will be 10 minus 1.927, and which comes out to be 8.073 volts. Okay, so that's the values of all the terminal currents and voltages. Now we go for the small signal parameters. So we have R1, which is beta 1 VT divided by IC1. VT over here is the thermal voltage, which is around 26 millivolts. So we substitute all the values, and you get R1 as 137.639 kilo ohm, and R2 is beta 2 into VT upon IC2. So if we substitute all the values, you will get it as R2 as 1.3627 kilo ohm. So after getting R1 and R2, our AC analysis starts. So for AC analysis, we have to estimate the input impedance given by Zin, output impedance given by Zout, the current gain AI, okay, and the total midband gain, that is the voltage gain. So for calculating the Zin and Zout, we have to at least see the small signal equivalent circuit. So this is the small signal equivalent circuit for the Darlington amplifier, which we have seen over here. Okay, so the small signal equivalent circuit will be like a BJT will be replaced by its hybrid pi model. So we have R pi and GM into V pi, and here we are defining something. Let me just minimize this slightly. I think now it is visible together. Okay, so here is my input. Here I have my two resistors R1 and R2 in parallel. My Q1 is replaced by R1 into G and a current source, dependent current source GM1 into V1. So basically what we are doing is, what I'm saying over here is, this diagram helps us to calculate Zin. Okay, so what is Zin? Zin will be R1 parallel to R2 parallel to Zi1. So what is Zi1? Zi1 will be R1. Now this is base current and this is emitter current. So whatever is below, you have to multiply it by 1 plus beta time. Okay, so it will be Zin will be R1 parallel to R2 parallel to Zi1. Okay, so let us see that now. Yeah, so Zin is R1 parallel to R2 parallel to Zi1. And what is Zi1 from this diagram? Zi1 is R1 plus Zi2 into 1 plus beta. Okay, that's what we have written over here. Zi1 is Zi2 into 1 plus beta plus R1. That's what is written over here. R1 plus this 1 plus beta times Zi2. So that's what we write over here. Zi1 is this. And what is Zi2? Zi2 will be R2 plus, because this is base current and this is emitter current. So it will be R2 plus 1 plus beta times Re. Now since beta 1 and beta 2 are same, so hence even if we don't call it beta 2 or beta 1, it's same. It's going to be same. Okay. So here we calculate Zi1 and Zi2. So Zi1 is R2 plus 1 plus beta times Re. That will be 102.36 kilo ohm. Zi1 will be Zi2 into 1 plus beta plus R1. So that number will come out to be 10.476 mega ohm. Now this is basically the input impedance of the Darlington pair. Okay, just looking into the transistor. So this is the input impedance of the Darlington pair. But we want the input impedance of the amplifier. So this 10.476 mega ohm will be parallel to R1 and R2. That's what we are doing over here. So Zin will be R1 parallel to R2 parallel to Zi1, which will be 100K parallel to 50K parallel to 10.476 mega ohms. If you work it out, you will get 33.22 kilo ohms. Okay, so the input impedance of the Darlington amplifier is very high, but when you connect it in the Darlington pair is very high. It is around 10.4 mega ohms. But when you connect it to a voltage divider configuration, it reduces slightly, which becomes 33.22 kilo ohms. Now, let's also simulate your Z out. So Z out, if you see carefully over here, let me reduce this to around 27, let's say. So if you see Z out, this will look, the impedance looking at the output emitter terminal. Okay, so that will be RE parallel to ZO2. Okay, for ZO2 you have to calculate ZO1 also. So your ZO1 will be, I'm not going into detail, I'm directly giving the formula, you can test it out. Okay, so this is your ZO2 looking into the emitter 2 terminal, and this is ZO1 which is looking into the emitter 1 terminal. Emitter terminal of Q1 transistor, and ZO2 is emitter terminal looking into the emitter terminal of Q2 transistor. And what is Q1 and Q2? This is what is Q1 and Q2. Okay, so I'm directly giving the formula here, I'm not explaining much in that. So ZO1 is R1 parallel to R2 plus R pi 1 divided by 1 plus beta 1. Okay, so this is ZO1. ZO1 will be R1 parallel to R2 plus R pi 1 divided by 1 plus beta. That's what is written over here. Okay, ZO2 will be ZO1 plus R pi 2 divided by 1 plus beta. Okay, so ZO1 will be ZO2 will be ZO1 plus R pi 2 divided by 1 plus beta. So why we are dividing by 1 plus beta? Because here the current is emitter and here the current is base, the base current. So if you want to convert emitter into base current, this relation is given by IE is equal to IB times divided by IB is equal to IE times divided by 1 plus beta. So that's why we are writing here divided by 1 plus beta everywhere. So ZO1, if you work out, you will get it as 1.693 kilo ohms, and ZO2 will be 30.25 ohms. Now what will be overall input output impedance? It will be RE parallel to ZO2. So that's what we get over here. So Z out will be equal to ZO2 parallel to RE, and which will come out to be very, very low number. So your ZO2 was how much? 30.25 ohms. Okay, so that in parallel to 1 case. So the ratio will be even smaller than 30 ohms. Okay, so it is 29.366 ohms, which is very low. So your Darlington amplifier has a very low output impedance. That's one of the major advantages. Now, let's check the current gain. Okay, so the current gain, it's pretty simple, straightforward. So AI1, which is the current gain of the first phase or the first transistor, you can say it is IE1 divided by IB1, and IE1 can be written as 1 plus beta times IB1. So IB1 cancels and you get 1 plus beta 1, which is 101. Similarly, IE2 is AI2 is IE2 divided by IB2, and again it is 101. So the current gain of the Darlington pair is just a multiplication of the two, AI1 into AI2, which is 10201. It is very, very high, around 10,200. But if you want to calculate the gain, of the entire amplifier, including the source, right? So AIS, we say from here, from this side, from the total gain, total current gain will be IO divided by II. Okay, so that's what we have to see. Right now, we have determined the current gain for the two transistors. Q1 and Q2, which is around 10,200. Now, let's calculate the gain for the overall circuit. So AIS will be IO divided by II, which can be written as IO divided by IB2 into IB2 divided by IB1 into IB1 divided by II. Okay, so here IB2 upon IB1 and IO upon IB2 is nothing but your AI1 and AI2 respectively. And IB1 upon II is nothing but RTH divided by RTH plus ZI1. Now this all can be determined from this diagram, and I'm not going into details over here. So we have over here AI, we have IB1, IE1, IB2, IE2, and IO. So we have to relate all these currents to get the overall current gain for the amplifier. Now let us go proceed further. So it will be IIS. The current gain of the amplifier will be AI1 into AI2 into RTH divided by RTH plus ZI1. So 101 into 101 into this ratio will give it to you 32.35. The total current gain of the amplifier has become 32.35 if you consider all the resistances also into consideration. Okay, so that's the current gain for the entire amplifier, your Darlington amplifier. Fine. Now, the midband gain is nothing but V out upon V in, correct? So let me go over here again in the diagram. So we have divided this into two phases. So there are two stages. The output of the first stage we have marked it as V1. So V1 divided by V in will give us AV1, and V out divided by V1 will give us AV2. The gain of the second stage is V out divided by V1, and the gain of the first stage is V1 divided by V in. Fine. So that's what we have done over here for the voltage gain. So AV mid will be V out upon V in, which can be written as V out upon V1 into V1 upon V in, which is AV1 into AV2, the gain of the first stage and the gain of the second stage. So the AV2 is V out upon V1, which can be written as IO upon IB2. You can refer the small signal equivalent circuit into RE upon ZI2. Okay. Now IO upon IB2 is nothing but AI2, and we know the value of RE, and we have already calculated the value of ZI2. So we substitute all the answers and you will get AV2 as 0.9867. AV2 is less than 1 and it is 0.9867. What about AV1? AV1 is V1 upon V in. That can be written as IE1 divided by IB1 into ZI2 divided by ZI1. Now this also I am not going to explain in detail how it comes, but the hint is that from this diagram, you have to relate it to this diagram. This diagram, this small signal equivalent circuit will give you all the answers. Okay. Let me go back to the formulas. So AV1 is AI1. The IE1 divided by IB1 is nothing but your AI1, and we have the value of ZI2 and ZI1. So we substitute them and you will get AV1 as 0.9868. So for the total gain, you have to multiply the two. So multiplication gives us 0.9868 into 0.9867, and the AV mid formula will, the value will be 0.9737. Okay. So the total voltage gain for this emitter follower Darlington pair is 0.9767. Okay. Now let us perform the LTspice simulation of the same circuit, and let us understand whether we are getting the simulated values closer to the calculated one. So let me keep this screen minimized a little. Okay. Let me bring it over here and let me reduce this slightly. Okay. So I have already made the circuit for your reference. This is the DC and the AC analysis of Darlington emitter follower amplifier. Okay, emitter follower circuit. So your CC1 is 10 microfarad, R1 is 100K, R2 is 50K, and Q1 and Q2 we have selected, and CC2 is around 10 microfarad, RE is 1 kilo ohm here it is. And here we are checking the output, and the supply is 10 volt, which is applied via the label terminal over here, VCC, as you can see clearly. So we have to determine all the DC parameters first. Okay, so let me maximize this part. We have already defined the dot model statement. Okay, so if you wish to know, we can do it again, but it's very straightforward. So you have to right click, go to draft, and go to your spice directive and type this code. There is dot model NPN1 NPN. IS is the reverse saturation current and BF is the beta. So the BF stands for beta, which is 100 for both the transistors. In fact, the parameters are almost same for both. Okay, so you just type your code over here, dot model and all that, and you click on OK. It will be pasted into the screen. So I've already done that. Next, I will go to simulate. Once all your connections are ready, all the coupling capacitors are connected, and the biasing circuits are ready, and you have selected this BJT from the component library. So you just have to type NPN. So this NPN BJT will come over here. Okay, so you have to drop the symbol over here, but do it perfectly as per the diagram. So in the diagram, as the connection is shown as it is, you do it over here. Okay. Now next is we go to simulate, click on run, and click on DC operating point. This will give us all the terminal voltages and terminal current. Now see, let me close this and go to view to spice error log. Okay, so these are the values which we are getting, and these are the values which we will set and confirm with our theoretical values. So let me just take the table over here. I've written down in the table. Yeah. So IV1 is 0.188 microampere in simulation, and in calculation also it's 0.1889 microampere. That's correct. So IB2 is 0.019 microampere, and in calculation also you are getting 0.01908 milliamp. I think it's milliampere, I guess. Yeah, I made a mistake over here. This polarity should be this unit should be milliamperes. Okay, this should be 0.019 milliampere. By calculation, it is 0.019 milliampere. By simulation, it should be, yeah, it should be 0.019 milliamperes. Okay, so please take care of it. And IC1 is 0.01889 milliampere, and by simulation it is 0.188. Okay, here it is 0.188 milliampere. IC2 will be 1.9 milliamperes in simulation, and by calculation it is 1.9079 milliamperes. So very close. And then IE2 will be the combination of both, and we are getting quite close answers over here. Okay, what will be VCE2? VCE2 is 8.08 by simulation, and by calculation we are getting 8.073. So quite close there. RPi1 is 137 kilo by simulation, and by calculation it is 137.369 639 kilo, and RPi2 is 1.36 kilo by simulation and 1.3627 kilometers by calculation. So all the DC parameters and a few small signal parameters are verified. So next we go for the input output characteristics. So what we will do is we'll deactivate this dot model now. It's not necessary now. And we have already applied sine wave of DC offset 0. Peak to peak amplitude is 40 millivolt and the frequency is 30 kilohertz. Let me remove this and click on OK. Now we have to label the input and output node. So I can label it as V in underscore your name. Okay. So let me place it here and let me place it here. And this you can rename it as V out. V out underscore your name. Okay. Also the Q1, Q2 transistor also we can do it. So Q1 underscore the name and Q2 underscore the name. Okay. So this will give us more unique circuits with our names on it. So we don't have to write them again and again. Okay. So we go to simulate. We click on run. It will ask for the transient response. So the time period will be 1 divided by 30 kilohertz. So that will be around, let me calculate, 0.03. Yeah. So we can give around 0.1 millisecond or so. Okay. So we can give around 0.1. That will give us 3 cycles almost. Okay. So 0 to 100 microseconds we got the cycle, and from here we have to plot the input and output. So right click, add phase input. Okay, and we can add a plane and plot the output. Okay, don't bother measuring. Now you will see that almost it's same. So the gain should be 1. No, it is appearing the gain is 1. In reality, it is not 1. In fact, in reality, if we merge them together, if you can see carefully, yeah, you can see output is slightly lesser than the input. So gain is slightly less than 1. Okay, so it's always better to plot separately. So this is my V in and this is from V out. So from visual inspection, if we see them, we can say, I mean, we say that they are almost same, but in reality they are not same. Okay, the amplitudes are not same. So hence, in order to do the perfect measurement, so we can use dot measure statement. So go to the schematic, right click, go to draft, go to spice director, and start writing dot measure. V in is the variable which you want to save the V in value. Peak to peak, V of the label which you have given. Okay, and if you go to the next line, we can copy the same statement, but we'll write V out. So this instead of V in, it will be V out, peak to peak. So what these statements are doing is we are measuring the peak to peak value of the V in and V out. And then I'm storing it in another variable that is gain, and I'm calling it as parent. It will be V out divided by V in. So I'm directly imposing the formula over here, and I pasted them on the screen. Okay, so with the help of these dot measure statements, we don't have to place the cursor on the output waveform and calculate them very precisely. The spice will directly give us the value. So let me simulate it again. And let me go over here, go to view and spice error log. Okay, so this is the gain which we are getting of this amplifier. Okay, now let me compare it with the gain which we got by calculation. So by calculation we are getting this 0.9737, and by simulation we are getting 0.973763. So exactly almost same up till 3 digits, or up till 4 digits. Up to 3 digits it's the same value. So the very accurate value the simulation is also giving us, and the calculation also is absolutely correct. So we close this. Next we want to find out. Next, what we want to find out is the Z in and Z out. Okay, that's the last thing. So for Z in, we can right click, then add the comment over here. So Z in will be the input impedance applied at the input base terminal of transistor 1. So it will be V in divided by I in, which can be written as V test divided by I test. Okay, so this is the value of input impedance. So what we do is we apply an external test source. First we remove this source. So removing means we will change to none and give AC amplitude as 1. Okay, that's what we do. And we have to rename this as test, and the node also we will rename it as test. Fine. And now we have to remove this dot chan because we are going to check the, and this also is not required. Okay, so this much is ready. We'll go to simulate, click on run. It will ask for the simulation. So we'll type on AC simulation, click on linear decade, number of points will be 100, start frequency will be 1K, end frequency will be 110 mega, let's say. Okay, so we directly got some graph. Now let me delete this. Okay, so here we don't have to plot the phase plot, so don't phase plot. And here we are getting the value of V out. So right click and click on the linear part. Okay, so let me check it again. Okay, okay. So what actually happened is we have just plotted the output. Okay, so here when we get this graph, when we get this blank screen, we have to right click, click on add trace, and do that V test divided by I test. Okay, that is mandatory. V test divided by I test, which will give us the input, the Z in part. So here we don't have to plot this phase angle, so I'm deleting this, and here right click and click on linear. So here it is. So remember the AC input was given as 30 kilohertz. So exactly at 30 kilohertz, you check this value. So this is around, you can say almost a straight line. So here it is. around 30 kilohertz, the value is 33.22 kilo ohms. Okay, so Zin is coming out to be 33.22 kilo ohms by simulation. So by simulation we are getting 33.227 kilo ohms, and by calculation we are getting 33.22 kilo ohms. So quite close. Next, what we do is we'll go over here, and instead of applying the source over here, we apply the source at the output terminal. So let me close this. Let me delete this node, and now I can directly place this at the output node. And here I can give the label again as test, because again the output impedance of the circuit is looking into the emitter terminal of transistor Q2. So let me just rewrite it. So Z out will be, the output impedance of the circuit will be V out divided by I out, which will be again equal to V test divided by I test. And then we click on OK. And now if we run this, it will directly give us the Z out value. Here it is. So Z out we have to test it at 30 kilohertz. So this is around 30, close to 30. Okay. And we are getting 29.3 ohms, as you can see very clearly, 29.3 ohms. Okay. And by Z out we got it as 29. Okay. Just wait a second. Yeah. So Z out we got it as 29.366 by calculation, and by simulation we are getting 29.3, as you can see very clearly. So Z out also is coming perfectly fine. Okay. And now if let me close this now. So this is how we have simulated the the DC and AC analysis of a Darlington emitter follower circuit. Okay, and we have seen all the parameters. Now the current gain total of the Darlington pair is 101 into 101. So why this is 101 into 101? Because we have just checked it is AI1 and AI2, which is 1 plus beta, and 1 plus beta it's a DC beta. Let's say it's AC beta. There is a two types of beta, AC beta and the DC beta. So AC and DC beta both same over here, 101. Okay. So while we were, let me show it to you one. So let me delete this dot AC, and let me show it to you one. The operating point. Okay. Let me close it and let me view the error log. Okay. So here if you see carefully, there is beta DC and beta AC. Now since both are same, around 100, here you can see it is 100, and beta AC is also 100. Okay, both are 100 for both the transistors, NPN1 and NPN2. So hence I have written over here AIT, which is the total current gain, is 101 into 101, which is 10,200, and similarly for a simulated value also it's 10,200. Okay, we can directly determine it from this spice error log only, which is just the beta AC only. Okay, that is 100 into around 1 plus beta AC, 1 plus beta and 1 plus beta. That will be 101 into 101. Okay, so here we have simulated everything. Now there is one small exercise which you have to do. So for this, you have to keep all the resistors values and the capacitors value being the same. Only change RE to 910. Now RE was given as around 1K. Make it slightly lesser, 910, and check which all parameters are getting affected, and note down only those parameters. And also mention, not only just note down, also mention whether it's increasing or decreasing, and try to understand why it might be increasing or why it might be decreasing as per the formula. Okay, so that's all for this session number 10, and we have seen the DC analysis, the AC analysis, and the Zin and Z out, that is the input impedance and the output impedance estimation for a Darlington emitter amplifier. So that's all for today. Next time we'll begin with some other topic. Until then, have a good day and thank you.